So the question is, how powerful is morphology? And like most questions in life, the answer is, what I always tell my kids, it depends. If you have nice, clean binary images, or even, I shouldn't say that, if your binary images behave exactly the way the 3 or 4 binary images you looked at when you designed the system were behaving, then things will be fine. So clean might be the wrong word. If it's, well, here it says almost clean. Let's just say that your binary images are sort of well behaved. So here's an example, and again, this comes from Linda Shapiro, all right? Here is an original binary image. And if I ask you to look at that quickly and ask you where are the faults in those gears, you would have to look at it for a long time. But if I show you this picture and I say, where are the faults in the gears? You would say, oh, I guess there's one here and there's one there. And now when you look at it, you see, oh yeah, there really is. There's a tooth missing from the gears. So the question is, how did they do that? So again, I'm not going to go into too much of the detail. I'm just going to show you this set of images. It's all on one page. That's the sequence of operations, and I'll just describe them briefly, okay? So here was their original picture that I showed you. Basically, over here, they were looking for places that had a ring that would be essentially black like this, white out here. And remember I was telling you about don't care pixels? You know, don't care in there, and of a particular shape, a particular size. And the only pixels that lit up were these guys. Okay? All right, well, that's fine. And then you say, okay, I'm going to take those and I'm just going to dilate them by something called a hole mask, which is just this basic shape. All right? So you realize what you end up with is just the holes filled up. Well, if I OR this plus this, I get that. So voila, I have filled the holes of my gear. Okay, great. Then what I can do is I can essentially do the same trick again of removing pixels that basically have with a structuring element like that. So I find every place where a structuring element like that fits, and that will be able to pull out these middle parts, and then I can dilate the edge, and I end up with this thing that looks like that. Great. That's sort of a bound around the edge that's thicker than the edge. If I AND these two things, so it's an AND, I get just the teeth. Okay, that's what's shown there. And also, you'll also notice we're starting to see there's that gap right there because that's where the teeth are missing. All right? Well, what I can do is I can dilate that by something that has the size of the tip. And if I run that around here, I end up filling everything except where that gap is, both here and there. And then given those, I can do, in fact, the result is just it's got this thing called defect Q. That's just this little round ball. Basically, the operation is exactly as here. It's B7, right, minus B9 here, dilated by the defect Q, ORed back with B9, and I get this, okay? So would I expect you to implement something like that? I don't know. The point is that with these relatively simple low-level mathematical operations, you can do a relatively sophisticated shape analysis if you have the particular shape that if you know the particular shape that you want to deal with and the particular types of defect sizes, for example, you wanted to find. So there are other operations that you can do. Here's just a list of things that you might compute. These are shape descriptors of binary blobs. And like I said, this used to be a very important part of computer vision, especially in assembly or machine vision of inspecting 2D parts. And for those particular applications, it still is.